Hello, welcome back. We're going to continue our discussion of proton therapy and carbon beams as well. In our last video, we looked for a long time at this curve, the depth dose curve for proton beam, the spread out Bragg peak, and so on. And now we're going to get into how you use this in practical applications. I want to start with talking about how you report dose from a proton beam. Here we go. In the last video, we talked extensively about this depth dose curve and the spread out Bragg peak. And now we come to the issue of how to talk about dose and how to report it. First, let's consider the relative biological effect of the proton beam, the RBE. So there's quite a bit of data on this, but the bottom line is that the ICRU 78 recommends that we're going to use a constant value for RBE of 1.1 for the proton beam. Now, it's a pretty gross simplification. There is data to indicate that near the end of the spread out Bragg peak, where the energy gets low and the LET gets high, the RBE is going to go up by 5-10%, maybe more. Depends on the tissue type and so on. But this is what they're advocating. Then how do you report the dose? So you'll see different units used. So you'll see like cobalt gray equivalent, CGE, as the dose reported for proton therapy beams. You'll also see gray equivalent, GYE, and then sort of like written differently with a script like this. So these are all now considered not SI units, and ICRU 78 is saying we should not use these, and instead we should just call this dose subscript RBE for the cobalt beam. And so you would report this. So this is maybe semantics, but anyway, the point being that you need to multiply it by some factor to get a weighted dose. All right, now we're going to talk about treatment planning, and in particular look at some of the issues in proton therapy that are quite different from photon therapy. First of all, the way that margins are handled is different. In X-ray therapy, typically the margin would be uniform around a tumor. In proton therapy, that's not true. There's actually an asymmetric expansion of the margin in the beam direction. And you have to be careful how you use these margins to make sure you hit the tumor. What accounts for this asymmetric margin is uncertainties. These include the CT numbers, stopping powers, and uncertainties in the range of the proton. And so in the end, what you do is end up adding a margin that's extra in the distal aspect. And so if you point the beam in a different direction, the margin will look different. Here's the typical formula that's used. 3.5% times the distance of the CTV in the distal range, and then a little extra buffer. And this varies a little bit between centers, but it's typically like this. Other considerations: motion is more complex with proton therapy, can be more complex than with photon therapy. We talked about the relative biological effect and possible end-of-range effects. And then anatomical changes. For example, if a patient loses weight or tumor shrinks, that can have a big effect on the proton therapy if the range of the proton beam is changed. And then IGRT technologies differ somewhat. This is an evolving topic, but some proton therapy centers up to date have really had very limited capabilities in terms of volumetric imaging, typically without cone beam CT or some of the other modalities. So let's move on to discuss quality assurance measures in proton therapy. Again, these are somewhat different than photon therapy. What's different? Well, for one, often in these pencil beam scanning systems, you have 1,000 spots delivered in 60 seconds. And you need to verify the location, the size, and the depth of each of those spots. So that's a challenge. And also, there can be very high dose rates, over 1,000 gray per minute in each spot. That makes it challenging to use detectors sometimes. Also, as we discussed, this SOBP is created dynamically with a spinning device, and so you can't use typically a scanning system. So, the normal way we would acquire data might be to put a water tank in the beam, move a detector around through the radiation field and measure it. Well, that doesn't work if your beam is moving dynamically. So there are specialized equipment that are used in proton therapy QA. This is one example. It's a water equivalent tissue. It has 180 parallel plate ion chambers, and you can get a field size of 10 by 10. This one is called the zebra. There's also the giraffe. That's slightly different, same idea. But it's a layer of detectors that are acquiring data simultaneously as the beam is on. Here's another type of device, the matrix array and ion chamber array with 1,000 ion chambers used for daily QA. There's another device called the Matrix 1, which is especially designed to handle those super high dose rates that come in the IBA system. And these can also be used for patient-specific QA for pencil beam scanning. Unlike photon therapy, every patient typically needs a QA. Here are some QA that's done on a daily basis. So this is more extensive than what you see with photon therapy. Here's a check with the matrix device, the ion chamber array. So you can check the constancy of output, delivering different standard fields. You can look at the spots to look at the position, the centroid of those spots. Here's another type of equipment, a scintillating detector, 30 by 30 cm in a very high resolution. Again, this can be used for patient-specific QA. Here's a type of test that's done monthly. So you'll look at the spot location and the size and the symmetry of each spot, and you'll scan it across the field at different locations. What I'm showing here is a plot for a low-energy beam. Here's the same plot for a high-energy beam. You'll note that the spot size is energy-dependent. Interestingly, the higher energies have larger spots. You can think about that. All treatments need patient-specific QA. So it's as if everybody's getting IMRT. And so there's all the overhead and procedures around that. Now I'd like to talk about radiotherapy with carbon ion beams. Carbon, of course, is much heavier than a proton. There are 12 protons in a carbon nucleus. So the physics of the interaction of this beam is going to be different. Now, I'm going to focus on carbon, but it's actually a little more general when you talk about radiotherapy with heavy ion beams. And different species can be used. So we're going to talk about carbon, but you could also have helium. And then you have some that are heavier than carbon. You have neon, silicon, argon. And those are even more rarely used, but we're focusing on carbon because that's the most common one right now. So to understand this, let me walk through some data. This is a simulation and measurements of a proton beam at 62 MeV. It's sort of a strange energy, but this was a lab system that these particular authors were looking at. But there are many such studies, so this is just for illustration. So first, let's look at this curve. So there's the fluence of the beam of the protons, number of protons per centimeter squared per second, let's say. As you go down in depth, it reduces the protons that are removed from the beam as they interact. Notice this is interesting. The fluence does not go down quasi-exponentially as it does in a photon beam. It's more linear until you get to the end. Then there's another curve here. This green I'm drawing here, this is dose, and they've done both measured dose in an experiment and also simulated through Monte Carlo with J04. And then the final curve you have here is LET. So it's LET dose, means dose-weighted LET. So the LET goes up until the end of the beam where it stops and there's no more beam left. And then you'll notice they actually have two curves for LET. So just to make this clear, the pluses here are from secondary particles. So not the primary proton beam, but mostly other protons that are created from the primary beam. So they're scattered, they're lower energy, they have higher LET, and also there's fewer of them, and they're more important near the entrance. So this is LET in units of keV per micron, which is a typical unit. Let's look at the scale here. So it starts at about 2 keV per micron. End of the Bragg peak goes up to about 35 keV per micron. So that range will be important later as we talk about carbon, where it's going to be much larger. Here, the LET is relatively low, except right in this small region right at the very end of the Bragg peak. All right, now let's look at what this looks like for a carbon ion therapy beam. We're going to use, from the study, they use an energy of 62 MeV per nucleon. So that's how you write this. It's the MeV per number of nucleons. Remember, nucleons are protons plus neutrons. So we have first the fluence, again, falling roughly linearly until the end of the beam. Remember, that's, again, quite different than for photons. Here's the dose in green. Again, it goes up, and there's a Bragg peak. These are charged particles, just like the proton, heavy charged particles. So you're going to see a Bragg peak, and it's bigger. And then here's LET in red, and it goes up until you get to the end of the beam. Now, LET is linear energy transfer, right? So now the end of this I actually didn't quite draw right. So there's actually some dose beyond the Bragg peak, and these particles have high LET. These are called fragments. So fragments means nuclear fragments from non-elastic scattering processes where the nuclei are fragmented. And that gives you some dose beyond the Bragg peak. And it will be even bigger with a higher energy beam. Okay, so LET, keV per micron. And let's look at the scale here. It's different than before. See, it starts relatively high here and goes up, and it goes really high. This goes up to 900 keV per micron. So these are very high LET particles compared to the proton. And they get especially high LET at the end of the Bragg peak range. So the biological effects of that are going to be different. Another important difference between a proton and a heavy ion beam is the penumbra. So the heavy ion beam typically has a penumbra that's much smaller than a proton beam, and that's an advantage. And it's beyond the scope to really talk about that in detail, but if you think about the analogy of a pea versus a bowling ball, if the bowling ball is a proton, well, the carbon nucleus is 12 times as many protons and neutrons also, and so it goes in even straighter lines as it goes through tissue, and there's less multiple Coulomb scattering. Let's talk about the relative biological effect of heavy ion beams. They have a bigger RBE compared to proton or photon beams. So let me try to explain some of the reasons behind it. Here's some numbers. The photon beams have a low LET and an RBE of 1. Proton beams have a little bit higher LET, especially at the end of the Bragg peak. But in general, we would say that RBE is 1.1. A little bit higher than photons. Now, the LET of a carbon beam is a lot higher, 100 keV per micron, and also, importantly, it varies greatly with depth, as we saw. Now, correspondingly, the RBE can be larger, 3 or even more. And there's some indication that as you go up above 100 keV per micron, the RBE dips down again, but that's not 100% consensus around that. So let me try to explain this linkage between LET and RBE. So we'll consider a cancer cell here. And let's say the size of that cancer cell, varies, but let's say it's 20 microns across. And then, of course, inside is the nucleus, and that has the DNA, of course. And let's say it's 5 microns. So that gives you a sense of the scale. Now, in the case of a photon beam, the physical dose deposition is a photon scatters with an electron. That's in the MeV range, and so the range of that is in centimeters. So there's this overall bath of electrons And so it's relatively uniform, much larger than the scale of the cell. And there's no kind of localized deposition. So that's very different than a high LET particle. And let me show what it looks like for high LET. So here you have a particle coming in, and it interacts at a particular point, and the dose deposition is very localized. The region around where the effect is very small. It can be even a few microns or even smaller, where effectively you're depositing the dose. And then another particle comes in, interacts here. Okay, but the region where the dose deposition is very localized. So you've got these small points that come at different random locations in the cell, depending on where the interactions are. So really that's your difference at the microscopic level of high LET versus low LET is the track structure and really the density of damage that happens. And that leads to a different molecular response in the cell. And in particular, the response to DNA double-strand breaks and the repair of those. Now, of course, this has been studied extensively over time, and there are some things we know about this. We can say that the number of strand breaks per unit length of the chromatin is roughly independent of LET. So that's not really an explanation for this. But it is different. The spacing of the double-strand breaks is different in high LET versus low. And also in high LET, you have clustered lesions, so clustered along the DNA strands, and the repair of those is much more difficult for the cell. So these are some of the effects that create a higher RBE at these higher linear energy transfer values. So the end result of all this then is that physical dose and biological dose don't track well together. So here, if you make a flat-topped SOBP with carbon beam, and the physical dose is flat, is shown in black, the RBE is varying a lot, and this is the simulations typically would look like this. So if you weight the physical dose by the RBE, the biological dose is quite uneven for this type of treatment. Actually, RBE effects become extremely important to include in heavy ion therapy treatment planning. All right, that concludes our brief foray into the world of proton beams and ion beams. I'm going to leave you with a little bit of further reading. This is a vast topic area, but fortunately there are some great resources to learn more. And with that, we'll conclude. I hope this provides a foundation. This is a modality that is very complex, but is going to become more widespread and available and accessible in the coming years. So it's good to understand at some level. Thank you.